So we would like to find the linear approximation to the function f of x, y, z equals e to the x squared minus y plus 2z centered at the point 3, 5, -2. And we would like to use that in order to estimate the output of the function at a neighboring point to that center. So let's start by recalling the theoretical basis of what we're trying to do. So in general, we can give the formula of the linear approximation. So the linear approximation to the function f of x, y, z around the point ABC is given by the following formula. So g of x, y, z is equal to the value of the function, the output of the function at the point under question, the center of the approximation as we call it, and then we take each partial derivative and multiply it by the variable minus the component of the point at that particular position. So it's really a first degree polynomial that shares the same value of the function and values for the first partial derivatives at that point. It's also the first Taylor polynomial, if you like, for our function. And basically, as far as the approximation is concerned, what we can say is that if you have a point, so if A1, B1, C1 is close to ABC, then the value at that point, at that other point, is approximately equal to the value of the linear approximation at the same point. One can go further here and actually give estimates of the error, but this is not what we want to do here. Okay, so at this point, we would like to proceed with the solution and just simply find the formula for the linear approximation, and to do so, we need to find the partial derivatives. Equivalently, it's the same as finding the gradient, but there's no need to even reference the gradient explicitly. So let's begin by finding the value at the point under question. So that would be e to the 3 squared, which is 9 minus 5, which is 4, plus 2 times -2, so minus 4, e to the 0, also known as 1. Okay, so this is very convenient. Actually, that's why the function was selected, so that it gives us convenient values at the center of the approximation, which actually makes sense. I mean, you want to use a point where computations are simple in order to compute the output at a point where computations may not be that simple. Anyhow, let's find the partial derivative with respect to x. We need to know that the derivative of the exponential function is itself, which means, thanks to the chain rule, e to some quantity has derivative equal to e to the same quantity times the derivative of that quantity. So in our case, we need to multiply by the derivative of the exponent with respect to x, and that's 2x, because we consider y and z to be constant. And of course, if we plug in at the point under question, we're going to simplify, find e to the 0 times 2 times 3 equal to 6. And let's do the partial derivative with respect to y. So this will be e to the x squared minus y plus 2z times -1, again by the chain rule. And if we plug in the point under equation, then we're going to get e to the 0 times -1, which is -1. And f partial derivative with respect to z will be e to the x squared minus y plus 2z times simply 2, which is the partial derivative of the exponent with respect to z. So f sub z at 3, 5, -2 will be e to the 0 times 2, which is of course 2. And now we can put together the formula for the linear approximation. So we have that g of x, y, z is going to be, let's write once the formula down for the specific point. We could do the substitution of the values right away, but let's just see it once more so that visually it can stay with us. It's a very simple formula that applies to any number of variables. And again, like I said, the idea behind it is to create a linear expression in x, y, z that gives the same values and for the function and the first partial derivatives. And now if we plug in the specific values, we're going to find 1 plus 6 times x minus 3 plus -1 times y minus 5 plus 2 times z plus 2. And that's it. That's our formula. So the linear approximation is equal to this. Okay, and we have one more step in our problem. We would like to estimate f of 2.9, 4.9, 1.9, and this is approximately equal to g at the same numbers, evaluated at the same numbers. And let's try to be careful with this simple computation. It's when the computation is simple that one makes mistakes. So this is 1 plus 6 times -0.1 sorry about this. Plus -1, which is what the derivative is with respect to y times. And now we have to do 4.9 minus 5, which is again -0.1. And plus 2 times 0.1, which is -1.9 plus 2. Okay, so how much do we get here? We get 1 minus 6 times 0.1. 2 minus give us a plus, so that's plus 0.1. And finally plus 2 times 0.1. So how many 0.1s do we have? We have -6 plus 3, that's -3. So 1 minus 3 times 0.1, which is 0.7. And that's our final answer. That's our estimate for the output of the function at this point. That's all. Thanks for watching.